Our universe's origin story is missing entire chapters. We are about to uncover 25 forgotten facts, pieces of the cosmic puzzle that challenge everything you thought you knew. This is not a dry history lesson, but a cosmic detective story where we will dig up clues buried by time and mainstream science. By the end, you will see the Big Bang, cosmic inflation, and even the question of what came before in a completely new light. We will explore how the entire cosmos was once smaller than an atom, and why we may never know its true beginning. What part of the universe's hidden past are you most curious to uncover? That first fraction of a second was not a moment of calm. The universe began not with a bang you could hear, but with space itself unfolding at a speed beyond comprehension. We call this the Planck epoch, a time so early that the entire cosmos was compressed into a volume trillions of times smaller than a single atom. Think of it not as a tiny dot in empty space, but as space, a seething, chaotic sea of pure potential. The temperature was beyond any number we can truly grasp, a number with 32 zeros after it. In this unimaginable environment, the rules of physics as we know them simply broke down. Gravity, the force that holds planets together, was not a separate entity. It was fused with electromagnetism and the nuclear forces into one single, primordial superforce. Picture the universe not as a collection of particles, but as a single, unified field, a roiling ocean of energy where time and space lost their distinct meanings. This was a reality where matter and energy were interchangeable, constantly flashing in and out of existence. It is a realm we can only describe through mathematics, a place where our familiar concepts of before and after, here and there, cease to have any meaning at all. This single, unified force held the blueprint for everything that would ever be, all the stars, galaxies, and life itself, locked within its incredible, unstable energy. But that unified, seething energy had to cool. As the universe expanded and chilled, it reached a critical milestone, releasing the afterglow we now call the cosmic microwave background. This was not the start of a bright new day, however. It was the beginning of a profound and silent night. For hundreds of millions of years, the cosmos was plunged into an era of total blackness, a true cosmic dark age. Imagine a universe with no stars, no galaxies, and no light sources of any kind. Space was filled with a silent, featureless fog of neutral hydrogen and helium gas, a primordial mist that absorbed any radiation trying to pass through it. It was a realm of pure potential, holding all the ingredients for creation, yet existing in a state of profound stillness and shadow. This immense, dark ocean of gas was the nursery for everything to come, a quiet stage being set for a dramatic entrance. The end of this darkness was not a gentle dawn. It began with a slow, relentless process, the pull of gravity acting on tiny ripples left over from the Big Bang. Over eons, these slight density variations caused vast clouds of gas to begin collapsing under their own weight, forming the very first proto-galaxies. Deep within these swirling structures, the first stars were born. These were not like the stars we see today. Known as population 3 stars, they were behemoths, hundreds of times more massive than our Sun. They were also pure, composed only of hydrogen and helium, the pristine elements forged in the Big Bang. Their purity made them incredibly hot, intensely bright, and tragically short-lived. They burned through their nuclear fuel in only a few million years, a mere blink in cosmic time. Their deaths were as spectacular as their births. These monstrous stars did not fade away. They ended their lives in cataclysmic supernova explosions of unimaginable power. This violent sacrifice was the key to our own existence. Within the furnaces of their cores and in the fury of their explosions, they forged the universe's first heavy elements, atoms like carbon, oxygen, and iron. For the first time, the basic building blocks of planets, oceans, and life itself were scattered into the cosmic void. The Dark Age was over, replaced by a new dawn illuminated by the first brilliant pinpricks of light, a light that carried within it the seeds of everything we know. This incredible forging of the first elements, however, depended on a cosmic setup that was almost perfectly smooth. How did a universe born in unimaginable chaos become so uniform? The answer lies in an even earlier event, a brief and violent growth spurt known as cosmic inflation. In the first trillionth of a trillionth of a trillionth of a second, the fabric of space itself did not just expand, it exploded outward at a speed far greater than light. Picture a single microscopic patch of that primordial energy, and then in an instant, it inflates to become larger than our entire observable universe. This exponential stretching ironed out all the wrinkles. Any large clumps or drastic temperature differences were stretched into a smooth, flat, and uniform cosmos, creating the perfect conditions for galaxies to form billions of years later. But this process came with a profound cost. That violent stretching was so extreme that it washed away all the original details. Any information about what existed before inflation, the universe's true initial conditions, was effectively erased. It is like taking a detailed drawing and stretching it so far in every direction that the image becomes a featureless blank slate. This is why we can only speculate about what came before the Big Bang or what triggered our universe into being. Cosmic inflation wiped the cosmic hard drive clean, leaving us with a fundamental and perhaps permanent limit to our knowledge. We are left staring at a smooth, uniform sky, forever wondering what was written in the universe's very first moments. This smooth, uniform cosmos we observe is built upon a profound and unsettling secret. The atoms that make up our bodies, our planet, and every star we can see are just a tiny fraction of what actually exists. In fact, everything we consider to be normal matter, the stuff of planets and people, accounts for a mere 5% of the entire universe. The remaining 95% is composed of two shadowy, invisible components we call dark matter and dark energy. Let us start with dark matter, which makes up about 27% of the cosmos. We cannot see it, touch it, or detect it with any of our instruments in a direct way because it does not interact with light at all. It does not emit, absorb, or reflect it, so how do we know it is there? We observe its immense gravitational pull. The stars at the outer edges of spiral galaxies are orbiting so fast that they should be flung off into deep space like mud flying from a spinning tire. The only thing holding these galaxies together is the gravitational grip of an enormous, unseen mass, a vast halo of dark matter that surrounds each galaxy like an invisible skeleton. Without this cosmic scaffolding, galaxies like our own Milky Way would have torn themselves apart long ago. The other 68% of the universe is an even deeper mystery, dark energy. This is not matter at all, but a repulsive force woven into the fabric of space itself. In the late 1990s, astronomers made a shocking discovery. They found that the expansion of the universe is not slowing down due to gravity, as everyone expected. It is speeding up. Something is actively pushing galaxies apart from one another at an ever-increasing rate, and we call that something dark energy. Its origin and true nature are completely unknown. It acts as a kind of anti-gravity, a force of cosmic repulsion that seems to be winning the long-term battle against the attractive pull of gravity. So the universe we thought we knew, filled with glittering galaxies, is really just a collection of visible islands floating in a vast, dark ocean of two substances we do not understand. This means we are surrounded by and made from a rare and exotic form of matter, while the true rulers of the cosmos remain utterly hidden from our view. This hidden cosmic rulebook, the one dark matter and dark energy seem to follow, might not have been written in stone from the very beginning. We take for granted that the fundamental constants of nature, numbers like the speed of light or the strength of gravity, are immutable and unchanging. But what if the rulebook itself has a history? Some of the most compelling theories in cosmology suggest that in the ultra-high energy frenzy of the universe's first moments, these laws were not yet fixed. The strength of the forces that bind atoms or the mass of an electron might have been different, slowly settling into the values we measure today as the cosmos cooled and expanded. Imagine a universe where the dials on reality's control panel were still being adjusted. A tiny shift in the strength of the nuclear force, for instance, would have had catastrophic consequences. If it were just a few percent stronger, all the hydrogen in the early universe would have fused into helium almost instantly, leaving no fuel for the first stars. If it were slightly weaker, the complex elements necessary for life might never have formed at all. The fact that we exist in a universe so finely tuned for complexity suggests something profound. The constants appear to be set to very specific values that allow for galaxies, stars, planets, and life. This delicate balance is one of cosmology's greatest mysteries. Is it just a staggering coincidence, or is there a reason behind the settings? Scientists are actively hunting for clues that these laws might have slowly drifted over cosmic time. They study the light from incredibly distant quasars, the brilliant cores of ancient galaxies, whose light has been traveling for billions of years. By analyzing the precise absorption lines in this ancient light, they can check if the fine structure constant, which governs the strength of electromagnetic interactions, was slightly different in the distant past. Other researchers scour the faint patterns in the cosmic microwave background, looking for any imprint of a time when physics was not what it is today. Finding even a hint of variation would revolutionize our understanding of reality. It would mean that the laws we consider eternal are not the universe's final word, but were themselves forged in the fire of creation, a dynamic product of the cosmos's own dramatic origin story. Perhaps the universe's rulebook was never meant to be permanent. This idea that the laws of physics might have evolved leads us to an even more radical possibility. The Big Bang may not have been a true beginning at all. Instead of a singular moment of creation from nothing, our universe could have been born from the death of a previous cosmos in an event known as the Big Bounce. In this cyclic model, the cosmos has no start and no end. It undergoes endless cycles of expansion and contraction, like a cosmic lung breathing in and out for all eternity. Our own expanding universe would simply be one phase in this infinite rhythm, following a period when a previous universe collapsed under its own gravity. This idea elegantly sidesteps one of the most troubling aspects of the classic Big Bang theory, the initial singularity. A singularity is a point of infinite density and temperature where the known laws of physics completely break down. It is a place where science, as we understand it, simply stops. The Big Bounce model, particularly in a framework called loop quantum cosmology, uses the principles of quantum gravity to propose a solution. Instead of collapsing into an infinitely dense point, the previous universe would have reached a maximum density, a point where the repulsive force of quantum gravity would become overwhelmingly powerful. Think of it not as a catastrophic crunch, but as a cosmic rebound. A super-compressed universe would hit a quantum wall and spring back outward, initiating the expansion phase we observe today. This bounce would have reset the cosmic conditions, potentially explaining the smoothness and uniformity we see in the cosmic microwave background. The violent, exponential expansion of inflation could have been a consequence of this rebound, a great smoothing out after the bounce. Scientists are now actively searching for any faint trace, any scar left behind from that pre-bounce universe. They meticulously analyze the cosmic microwave background, that fossilized light from the early cosmos, looking for subtle statistical anomalies or specific patterns in the polarization of the light that standard inflation cannot explain. Finding such an imprint would be revolutionary. It would mean our universe is not a one-time event, but merely the current incarnation in an endless cycle of cosmic death and rebirth, a phoenix forever rising from its own ashes. This strange alignment in the ancient light of the cosmos has a name as dramatic as its implications, the axis of evil. When scientists created a full sky map of the cosmic microwave background, they expected to see a random, featureless scatter of hot and cold spots, a perfect snapshot of infant universe chaos. Instead, they found something that sent a chill through the field of cosmology. The temperature fluctuations were not completely random. They appeared to be subtly aligned along a particular plane, a specific direction in space, as if the entire universe has a preferred axis. This is a direct challenge to one of the most sacred principles in all of science, the cosmological principle. This principle states that on a large scale, the universe is isotropic and homogeneous. It should look the same in every direction and have no special place, no center, and certainly no cosmic axis. The axis of evil suggests that on the largest scales we can observe, the universe might not be the same in all directions after all. Imagine looking at a vast, calm ocean and realizing all the waves are tilting slightly in one single direction. That is the level of unease this discovery has caused. The immediate reaction from many scientists was to search for a more mundane explanation. Could this be a systematic error, a ghost in the machine of our satellites? Perhaps our own solar system's motion through space is imprinting this pattern on the data, or maybe interstellar dust within our Milky Way is subtly distorting the view. Teams have checked and rechecked the data for over a decade, accounting for every known local influence, and the strange alignment stubbornly persists. This has forced cosmologists to consider far more radical ideas. Perhaps the universe itself is not uniform. Some theories suggest the fabric of space-time might be subtly twisted on a cosmic scale, a property known as anisotropy. Others propose that the early universe underwent a more complex form of inflation than we currently imagine, one that left behind a directional imprint. The most mind-bending possibility is that this axis is a shadow, a bruise left by a collision with another universe in the vast multiverse. While these ideas remain speculative, the axis of evil stands as a stark and humbling reminder. Our most fundamental assumptions about the cosmos are not yet set in stone, and the universe seems to enjoy presenting us with puzzles that defy our simplest expectations. That unsettling alignment in the cosmic background radiation hints at a cosmos governed by forces we are only beginning to perceive. The true depth of our misunderstanding was revealed in 1998, when two independent teams of astronomers made a discovery so shocking it would later earn them the Nobel Prize. They were measuring the distances to incredibly far-away supernovae, using these exploding stars as cosmic mile markers to track how the universe's expansion rate has changed over billions of years. Everyone expected to find that the pull of gravity was putting the brakes on the cosmos, slowing the expansion down over time. The data told a completely different story. The most distant supernovae were fainter than they should have been, meaning they were farther away than any model of a slowing expansion could explain. The universe was not slowing down at all. It was speeding up. Something was actively pushing galaxies apart, making the expansion of space itself accelerate with every passing moment. This mysterious culprit was given a name, dark energy. It is not a substance we can touch, but rather a property of empty space itself, a repulsive force that counteracts gravity's relentless pull. Think of it as an anti-gravity effect woven into the very fabric of the cosmos. This discovery completely overturned our forecast for the ultimate fate of the universe. Before this, scientists envisioned two possible endings: a big crunch where everything collapses back into a singularity, or a slow, cold fade as expansion gradually slowed to a halt. Now, a far more dramatic and lonely finale seems likely. If the acceleration continues unchecked, dark energy will eventually overwhelm all other forces. In a scenario called the Big Rip, the repulsive force would become so powerful that it would tear apart galaxies, then solar systems, then planets, and finally even atoms and nuclei themselves, shredding the very fabric of reality. A less violent but equally bleak outcome is a cosmic heat death, where the universe expands so rapidly that galaxies recede from one another faster than the speed of light. The sky would grow dark and empty, each island universe forever isolated in an immense, cold and silent void. This single discovery did not just add a new chapter to cosmology, it rewrote the entire final chapter, revealing a cosmos driven by a mysterious force that is, even now, pulling it apart. The discovery of dark energy revealed a cosmos racing toward an empty future, yet the very atoms telling this story carry a far more ancient and intimate history. Nearly every atom in your body, except for the hydrogen, was forged in the heart of a star that died billions of years ago. You are literally made of stardust. This is not a metaphor, it is the direct result of cosmic alchemy, a process called nucleosynthesis. In its first few minutes, the Big Bang produced only the simplest ingredients, a universe composed almost entirely of hydrogen and helium with a tiny trace of lithium. These were the only elements in existence for millions of years. They are the raw, primordial material of the cosmos. Everything else, every atom of carbon in your cells, every atom of oxygen you breathe, every speck of iron in your blood, had to be manufactured later, deep within the nuclear furnaces of stars. A star's life is a constant battle between the inward crush of gravity and the outward push of nuclear fusion. In the core of a star like our Sun, the immense pressure and heat fuse hydrogen atoms into helium, releasing the energy that makes stars shine. For more massive stars, the story does not end there. As they age and run out of hydrogen, their cores contract and grow even hotter, reaching temperatures high enough to fuse helium into carbon, and then carbon into even heavier elements like oxygen and neon. This layered fusion process builds elements like a cosmic onion, with iron eventually accumulating at the very center. Iron is a dead end for fusion. Unlike lighter elements, fusing iron does not release energy, it consumes it. The moment a massive star develops an iron core, its fate is sealed. The energy production stops and gravity wins in a single, catastrophic instant. The star collapses and then rebounds in a titanic supernova explosion, one of the most violent events in the universe. The blast unleashes a neutron storm so intense that in mere seconds it forges all the elements heavier than iron, like gold, silver, and uranium. The supernova then blasts this newly created, enriched material far out into space, scattering the stellar ashes across vast distances. These elements mix with clouds of primordial gas, creating the rich nebulae that will one day collapse to form new stars, new planets, and new life. Our own solar system coalesced from such a cloud, one that was seeded with the debris from countless generations of long-dead stars. So when you look up at the night sky, you are not just a distant observer. You are a part of that cosmos looking back at itself. The calcium in your bones, the nitrogen in your DNA, the oxygen filling your lungs, all of it was once inside a star that no longer exists. We are the universe become conscious, remembering its own spectacular and violent origins. This stardust that forms us occupies a tiny corner of a stage whose true size remains one of the universe's best-kept secrets. We speak of the entire cosmos, but what we can actually observe is just a small, illuminated bubble within a much greater, unseen whole. This bubble is called the observable universe, and it has a hard boundary about 46 billion light-years away in every direction. This limit is not a physical wall, but a horizon in time, a direct consequence of the universe's age and the finite speed of light. We cannot see beyond this point, not because there is nothing there, but because the light from those more distant regions simply has not had enough time to reach us in the nearly 14 billion years since the Big Bang. Everything within this sphere is causally connected to us, its story carried to our telescopes by ancient photons. Yet, the most profound implication of cosmic inflation is that this entire vast observable universe with its 2 trillion galaxies is likely just an infinitesimal speck. The entire universe, the totality of everything that exists, is almost certainly much, much larger and may in fact be truly infinite. If the whole universe is infinite, then our observable portion is like a single grain of sand on an endless beach. What makes this fact so humbling is the concept of causal disconnection. There are regions of space so far away that their light will never reach us, not even if we wait for all of eternity. This is because the space between us and them is expanding faster than light can travel across it. Those realms are forever beyond our view, their galaxies and potential histories completely inaccessible. They are part of the universe, yet they exist in a separate cosmic story, one we can never read. This means the grand cosmic narrative we piece together from our observations is just a local history, the tale of our own tiny neighborhood. The true, full scale of reality is fundamentally and permanently hidden, a silent, immense ocean surrounding our small island of light. Those vast cosmic structures, from glittering galaxies to immense superclusters, all trace their lineage back to a ghostly imprint from the quantum realm. This is one of the most profound connections in all of science, linking the very small to the very large. During that explosive period of cosmic inflation, the universe was not perfectly smooth at the quantum level. Empty space, even today, is not truly empty. It is a seething, bubbling foam where pairs of virtual particles constantly flicker into and out of existence. These are quantum fluctuations, tiny, temporary imbalances in energy. In the normal world, they are fleeting and insignificant, but during inflation, something extraordinary happened. The fabric of space was stretching so rapidly that these subatomic ripples did not have time to vanish. Instead, they were frozen in place and stretched to enormous astronomical sizes. Imagine a tiny, microscopic wrinkle on the surface of a balloon. Now imagine inflating that balloon to the size of the entire Earth. That tiny wrinkle becomes a massive, continent-spanning ridge. Inflation did exactly this to quantum jitters, magnifying them into the first large-scale variations in the density of the universe. These minute differences in density meant that some regions of the early cosmos had just a little more matter and energy than others. After inflation ended, gravity went to work on these subtle seeds. Over hundreds of millions of years, the slightly denser patches exerted a stronger gravitational pull, drawing in more and more gas from their surroundings. What began as a quantum whisper became a gravitational shout. The tiniest clumps grew into the first stars. Those stars gathered into galaxies, and galaxies themselves were pulled into the vast, web-like filaments and immense voids we see mapped across the sky today. The Great Wall of Galaxies, a structure hundreds of millions of light-years across, is a direct descendant of a random subatomic event. This means the entire cosmic architecture we observe, the grand stage upon which the history of the universe plays out, was predestined by random quantum dice rolls in the first fleeting moments of time. Your existence and the planet you stand on are only possible because of those ancient microscopic tremors in the fabric of reality. This cosmic architecture, born from quantum whispers, rests upon a foundation we take for granted, the steady flow of time. Yet time itself may be the most profound illusion of all. The startling truth is that time, as we know it, may have begun with the Big Bang. Our entire understanding of cause and effect, of a past leading to a present and a future, collapses at that initial moment. Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, works beautifully for the expanding universe. But when we rewind the cosmic film all the way back, the equations point to a singularity, a state of infinite density where the fabric of spacetime itself is crumpled into a meaningless point. At this singularity, the very concepts of before and after lose all meaning. Asking what happened before the Big Bang might be as nonsensical as asking what is north of the North Pole. On a globe, the North Pole is the definitive northernmost point. Every direction from it is south. There is no north of it. Similarly, the Big Bang may represent the ultimate beginning of time, a boundary where time itself was born. There simply was no before for anything to happen in. This idea challenges the core of human intuition. We are wired to perceive a linear timeline, a chain of events stretching backward forever. But the universe seems to operate under different rules at its origin. Some theories, like loop quantum cosmology, attempt to address this by proposing a quantum bridge, a bounce from a previous cosmic phase where time had a different character. Yet, even in these models, the classic flow of time as we experience it still finds its genesis in that transitional event. The fundamental nature of time's origin remains one of cosmology's deepest and most unsettling mysteries. It forces us to confront the possibility that causality, the principle that every effect has a cause, might not be a fundamental rule of reality, but merely an emergent property of the universe that blossomed after its own beginning. We are left staring into the abyss, not of empty space, but of timelessness, a state of existence our minds are fundamentally unequipped to comprehend. Even the steady flow of time depends on motion, and motion itself holds a cosmic secret. For centuries, we believed all motion was relative, that there was no way to define an absolute state of rest. A passenger on a smoothly moving train cannot prove they are moving without looking out the window, because the laws of physics work the same inside the train car as they do on the ground. Einstein enshrined this idea in his theory of relativity, declaring there is no preferred frame of reference in the universe, yet the cosmos itself provides one. The key is the cosmic microwave background, that ancient afterglow from the universe's infancy. This radiation fills all of space with an almost perfectly uniform temperature, a frigid 2.7 degrees above absolute zero. But it is not perfectly uniform. As our solar system moves through space, we are plowing through this sea of primordial light. This motion creates a Doppler shift, the same effect that makes a siren's pitch change as it races past you. In the direction we are heading, the CMB radiation appears very slightly warmer, compressed towards us. In the opposite direction from where we are receding, it appears just a fraction of a degree cooler, stretched out. This temperature difference creates a pattern known as the CMB dipole, a hot spot and a cold spot on opposite sides of the sky. By mapping this subtle imbalance, scientists have calculated our absolute velocity. Our entire solar system is racing towards the constellation Leo at a staggering 370 kilometers per second. This is our true motion, not relative to the Sun or the center of our galaxy, but relative to the rest frame of the universe as a whole, a frame defined by the very fabric of space-time left over from the Big Bang. This does not break Einstein's relativity, because this cosmic frame is not an inertial frame you can occupy, but it does give a profound new meaning to the phrase moving through the universe. We are not merely drifting, we are on a measurable, high-speed journey through the cosmos, with the oldest light in existence as our guide. Our absolute motion through the cosmos is measured against a backdrop of ancient light, but rewind far earlier, and the universe itself was a form of matter so alien it defies solidity. For the first few fleeting microseconds after the Big Bang, the cosmos was not filled with atoms or even the protons and neutrons that form them. It was an ocean of pure, unconfined chaos called a quark-gluon plasma. Imagine a universe so incredibly dense and hot that the fundamental bonds holding matter together were utterly dissolved. Quarks, the indivisible particles that make up protons and neutrons, and gluons, the particles that carry the strong nuclear force, could not combine. They existed as a seething, opaque soup, a primordial state where matter was not yet matter, but a collective, superheated fluid. This was not a gas or a liquid as we know them. It was a perfect, frictionless liquid, a substance so dense that even its constituent particles moved in a strange, unified harmony. In this extreme environment, the universe was completely opaque. Light could not travel freely as it was constantly scattered and absorbed by the dense, roiling sea of free quarks and gluons. This was reality before structure, a time when the very building blocks of atoms roamed unshackled. Then, in a critical transition, the universe expanded and cooled past a certain threshold. In a process known as hadronization, the quarks and gluons lost their freedom. The force between them, the strong nuclear force, suddenly became overwhelming, pulling them together and confining them into composite particles. Free quarks snapped into groups of three, forming the first protons and neutrons. The universe had cooled enough to allow the very first permanent pieces of atomic nuclei to congeal out of the formless plasma. This bizarre chapter is not just theoretical. Scientists at facilities like the Large Hadron Collider recreate these conditions for a fraction of a second. They smash heavy ions together at nearly the speed of light, generating temperatures over 100,000 times hotter than the sun's core. In the resulting microscopic fireballs, they observe the quark-gluon plasma forming and then cooling back into ordinary matter, giving us a direct glimpse into the universe's first moments. This violent, liquid beginning reveals that the solid, stable world we take for granted was born from a state of ultimate fluidity, a time when the rules of matter were written in fire. The geometry of the cosmos is a perfect flatness, a condition so precise it defies random chance. When cosmologists say the universe is flat, they are not describing its shape like a pancake. They are talking about its intrinsic geometry, the rules that govern the paths of light and the fabric of space itself on the grandest scales. In a flat universe, the angles of a triangle always add up to 180 degrees, and two parallel laser beams will never meet or diverge. They will stay perfectly parallel as they travel across billions of light years. This is the familiar geometry we learned in school, the rules of Euclid, and it turns out they apply to the entire observable cosmos. This flatness is not a trivial detail. It is a state of perfect balance on a cosmic knife edge. The density of matter and energy in the universe appears to be exactly at the critical value needed to achieve this flat geometry. If the density were even slightly higher, the universe would have a positive curvature like the surface of a sphere. In that closed universe, parallel beams of light would eventually converge, and the entire cosmos would have collapsed back on itself in a big crunch long before stars or life could ever form. Conversely, if the density were just a tiny bit lower, the universe would have a negative curvature like a saddle. There, parallel light beams would diverge, and space would have expanded so rapidly that matter would have been diluted into a near-perfect vacuum, preventing gravity from ever pulling gas together to form galaxies. Our existence hinges on the universe achieving this exact critical balance. The odds of this happening by accident are astronomically small. How did a universe born in chaos settle into such a perfectly tuned state? The leading explanation is, once again, the phenomenal stretching of cosmic inflation. Think of the universe before inflation as a tiny, wrinkled sphere. Inflation acted like a cosmic iron, stretching that sphere to an immense size. Just as the surface of the Earth appears flat to us standing on it, the entire observable universe appears flat because inflation stretched a tiny, primordial patch to a scale far larger than we can see. This process drove the geometry toward perfect flatness with incredible precision, smoothing out any initial curvature. The fact that we measure a flat universe today is one of the strongest pieces of evidence that inflation truly happened. It resolves the flatness problem, showing that the delicate balance we observe is not a bizarre coincidence but a direct prediction of the theory. Yet, this solution leaves us with a profound question. If inflation made the universe flat, what was its original geometry, its true shape before this cosmic ironing began? That initial curvature is another piece of information lost to the violent expansion, another secret from the first moments that we may never recover. This perfect cosmic flatness rests upon a foundation of matter, but that foundation is itself deeply unbalanced. One of the most persistent mysteries of the Big Bang is the simple fact that we are here at all. Our best theories tell us the initial explosion should have created a perfectly symmetrical cosmos with equal amounts of matter and antimatter. For every particle of matter born, a mirror particle of antimatter should have been born alongside it. When matter and antimatter meet, they annihilate each other in a flash of pure energy. So why did the universe not immediately self-destruct? A perfect symmetry would have led to total mutual annihilation, leaving behind a lifeless, empty cosmos of pure radiation. Clearly, that did not happen. Something in the early universe broke this perfect symmetry, tipping the scales just enough so that for every billion pairs of matter and antimatter particles that annihilated, a single solitary matter particle was left behind. That 1 in a billion survivor is the reason for everything we see, every star, planet, and living thing. The search for the mechanism behind this cosmic imbalance, called baryogenesis, has led to one of the most creative and bizarre ideas in all of cosmology. What if the symmetry was never actually broken? What if our universe does have a perfect mirror image, but we just cannot see it? This is the theory of a CPT symmetric universe. CPT stands for charge, parity, and time. It is a fundamental symmetry that physicists believe all physical laws must obey. The theory suggests that to preserve this perfect symmetry, the Big Bang must have created not one but two universes. Our own universe, expanding forward in time and made of matter, and a mirror anti-universe, expanding backwards in time from our perspective and composed entirely of antimatter. In this radical picture, the antimatter did not vanish. It simply went its own way, forming an entire cosmos that is, in a fundamental sense, a reflection of our own. From our point of view, it would appear to be running backwards in time, its Big Bang happening in our future. We are forever causally disconnected from this mirror realm, unable to see or touch it, yet its existence would perfectly explain why we find ourselves in a world of matter. It is an elegant, if highly speculative, solution. This idea demonstrates the extraordinary lengths to which cosmologists must go to solve a problem that strikes at the very heart of our existence. It forces us to confront the possibility that everything we know and see is just one half of a grander, hidden duality, an invisible twin universe of antimatter forever receding from our grasp. Our universe was once a roaring ocean of sound. Long before the first star ignited, the cosmos was filled with a deafening symphony of pressure waves crashing through the primordial plasma. For the first 380,000 years, the universe was so dense and hot that particles of light, photons, were hopelessly entangled with the first atoms, protons and neutrons. This thick, opaque soup was a perfect medium for sound. Gravitational pull from dark matter would try to clump matter together, while the intense radiation pressure from the trapped light would push it apart. This created a continuous push and pull, generating spherical pressure waves that raced outward at over half the speed of sound. These were not gentle vibrations but titanic compressions, true sonic booms on a cosmic scale. The entire universe was ringing like a bell. Then, in a single transformative moment, everything changed. As the universe expanded and cooled to around 3,000 degrees, electrons and protons finally combined to form stable, neutral hydrogen atoms. The photons, which had been constantly scattered by the charged plasma, were suddenly set free. The universe went from being opaque to transparent in an instant, and that first flash of released light is what we now detect as the cosmic microwave background. But the sound waves did not just vanish. At the precise moment of this decoupling, the waves were frozen in place. Their final, maximum compressions and rarefactions became permanently imprinted as tiny temperature differences in the CMB, a series of hot and cold spots on the sky. Cosmologists have measured these patterns with exquisite precision, and they reveal a series of distinct peaks like the harmonic notes of a musical chord. The scale of these peaks tells a detailed story. The first peak reveals the overall geometry of the universe, confirming its flatness. The second peak gives us the amount of ordinary matter in the cosmos. The third peak is sensitive to the density of dark matter. By reading this cosmic sheet music, scientists can determine the universe's composition, its age, and its rate of expansion with astonishing accuracy. The roar of creation has faded to a whisper, a fossilized echo in the microwave static that fills the void, a permanent record of the universe's first and only song. That cosmic symphony of sound was born from a vacuum we mistakenly think of as empty. The void of space is not a true void at all. It is, according to quantum field theory, a seething, bubbling arena of constant activity. What we perceive as nothingness is actually a foam of virtual particles that flicker into and out of existence in a fleeting dance with the laws of physics. These are not particles in the normal sense. They are particle-antiparticle pairs that borrow energy from the vacuum for an impossibly short time, only to annihilate each other and return the energy before the universe can notice the debt. This ceaseless creation and destruction is called quantum fluctuation, and it means that every single cubic centimeter of so-called empty space is a hotbed of transient, energetic life. We cannot see this directly, but we can observe its effects. A stunning demonstration is the Casimir effect. Imagine placing two perfectly smooth, uncharged metal plates extremely close together in a perfect vacuum, just a few nanometers apart. Classically, with nothing between them, nothing should happen, but in reality, a mysterious force pushes the plates together. Why? The answer lies in the quantum foam. The space outside the plates is vast, allowing for virtual particles of all wavelengths to pop into existence. The narrow gap between the plates, however, is so small that it only permits virtual particles with specific, shorter wavelengths to form. With more activity pushing on the plates from the outside than from the inside, the net result is an inward pressure. The plates are literally squeezed together by the restless energy of the vacuum itself. This seemingly obscure quantum quirk connects to the largest mystery of all, dark energy. One of the leading candidates for the force driving the universe's accelerated expansion is vacuum energy, the idea that empty space itself possesses a fundamental, repulsive energy density. If the vacuum is truly this dynamic sea of fluctuating energy, then perhaps the cumulative effect of all this activity across the entire cosmos is what is pushing galaxies apart. The calculation is not yet perfect, and the predicted energy is far greater than what we observe for dark energy, but the connection is profound. It suggests that the true engine of cosmic destiny may not be found in the glitter of stars, but in the hidden, vibrant hum of the nothingness between them. This vibrant cosmic hum, the very energy of the void, hints at a reality far stranger than we can perceive. The information that makes up our universe, from the spin of an electron to the swirl of a galaxy, might not be stored within the three-dimensional space we inhabit. Instead, it could be encoded on a distant two-dimensional surface like a cosmic DVD. This is the holographic principle, and it begins not with the universe but with the most enigmatic objects within it, black holes. When matter falls into a black hole, it vanishes behind the event horizon, seemingly lost forever. This presented a paradox because the laws of quantum mechanics state that information can never be truly destroyed. So where does the information go? The revolutionary insight was that all the information about the matter swallowed by the black hole is not stored in its hidden interior, but is somehow smeared and encoded on its two-dimensional event horizon, the point of no return. The entropy of a black hole, which is a measure of its information content, is proportional to the surface area of its event horizon, not the volume of the space inside. Think of it like this: a seemingly three-dimensional object, like a hologram on your credit card, gets all its depth and detail from a flat, two-dimensional image. In a similar, though far more fundamental way, a black hole's entire three-dimensional interior could be described by quantum data written on its two-dimensional surface. Now take this staggering idea and apply it to the entire cosmos. Some theoretical physicists propose that our entire observable universe operates on the same principle. The stars, planets, and our own conscious experiences could be a magnificent projection. The information for everything we see and feel might be encoded on a vast spherical shell at the very edge of our observable universe, the cosmological horizon. We are not living inside the projector, we are the movie being shown. If this is true, then our perception of a three-dimensional world is a magnificent, persistent illusion. The solidity of the floor beneath your feet, the vast depth of the night sky, it would all be a kind of cosmic trick, a hologram of breathtaking complexity and precision. While this remains a speculative theory, it forces a profound shift in how we view reality. The universe may not be built from tiny, solid points in space, but from intricate networks of information, a cosmic code whose true language is written on a boundary we can never reach. That first fragile bond, the beginning of all chemistry, was forged not on a planet but in the vast emptiness of space. After the formation of the first atoms, the universe was still a hostile place, far too hot and energetic for neutral atoms to simply link together. They were solitary islands, unable to connect, yet a crucial bridge was possible. Helium, the second element created, had two varieties. Most was neutral, but a fraction existed as ionized helium, atoms that had been stripped of one of their two electrons, giving them a positive charge. These loners found a partner in the most abundant particle in the cosmos, the single, lonely proton that is the nucleus of a hydrogen atom. Drawn together by their opposing charges, the ionized helium atom and the proton did something revolutionary. They shared the helium atom's one remaining electron, forming the very first molecule in existence, the helium hydride ion, or He+. This was not a stable union like the molecules we know today. It was incredibly fragile, easily torn apart by collisions or radiation, a fleeting handshake in the cosmic dark. For decades, this molecule was only a theoretical prediction, a ghost from the early universe that scientists were certain must have existed but could not find. Then, in 2019, using a sophisticated airborne observatory, astronomers finally detected its unique infrared signature in the turbulent gas of a planetary nebula. The discovery was a direct confirmation of a pivotal cosmic milestone. That simple, unstable molecule was the spark. It proved that chemical bonds could form in the void, opening a door that could never be closed. The formation of He+ began a cascade. It helped cool primordial gas clouds, and its existence paved the way for the formation of molecular hydrogen, the fuel for the first stars. From that single, tenuous bond, the entire roadmap to complexity was drawn, a path that would eventually lead to the water in our oceans and the carbon in our cells. All of chemistry, and thus all of life, began with that one quiet partnership in the dark. The cosmos is not a cold, empty void. It has a temperature, a faint but measurable warmth that permeates every cubic inch of space. This universal background radiation sits at a steady 2.7 Kelvin, which is a bone-chilling 270.45 degrees Celsius below zero. While that sounds impossibly cold to us in the grand scheme of the universe, it is a significant and telling warmth. This heat is not coming from stars or galaxies. It is the faded afterglow of the Big Bang itself, the cosmic microwave background, cooled and stretched by 14 billion years of expansion into the microwave part of the spectrum. Its discovery was one of the greatest accidents in scientific history. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, mysterious hiss in their massive horn antenna at Bell Labs in New Jersey. No matter where they pointed the antenna, this constant, uniform noise remained. They scrubbed the equipment clean, even evicting a pair of pigeons and their droppings, which they jokingly referred to as a white dielectric material. Yet the noise persisted. This annoying static was not a technical fault. It was the whisper of creation, the oldest light in the universe reaching their antenna from all directions at once. That persistent hiss was the sound of the cosmos cooling down from its fiery birth. What Penzias and Wilson had stumbled upon was a snapshot of the universe at the tender age of 380,000 years. This is the moment when the expanding cosmos cooled enough for electrons and protons to combine into stable atoms, a pivotal event called recombination. Before this, the universe was an opaque fog of charged particles trapping light. The moment atoms formed, space became transparent, and that first flash of light was set free. We now detect that flash as the cosmic microwave background, a fossilized image of the infant universe. Its existence and its nearly perfect uniformity became the single most compelling piece of evidence for the Big Bang theory, decisively defeating the rival steady-state model. This universal temperature gives the cosmos a thermal character, a baseline warmth against which all other heat is measured. It means that true, absolute cold is impossible to find, because even in the deepest voids between galaxies, space itself is gently warmed by the faint, enduring echo of how it all began. The warmth of that cosmic echo might not be a unique signature. Our entire universe, with its finely tuned laws and glittering galaxies, could be just a single bubble in an infinite cosmic foam. This is the multiverse hypothesis, a speculative but scientifically grounded idea that redefines reality itself. The strongest argument for it comes from a variation of cosmic inflation known as eternal inflation. The theory suggests that the inflationary process that smoothed our universe never truly stopped everywhere. Instead, it stopped in our local patch, creating our Big Bang and our observable universe. But in the greater meta-realm beyond our horizon, the hyper-fast expansion of space continues eternally. In this eternally inflating background, random quantum fluctuations can trigger the formation of new bubble universes like ours. These bubbles nucleate, grow, and develop their own internal laws of physics as they cool. Picture a pot of boiling water on an infinite stove. Our universe is one single bubble rising to the surface, while countless others are forming and popping all around us in a frothing sea of creation. Each of these bubbles could be a separate universe, forever causally disconnected from our own, with its own unique properties. String theory, a candidate for a theory of everything, adds another layer to this staggering possibility. It suggests the existence of a vast landscape of possible vacuum states. Each stable vacuum corresponds to a different set of physical laws and constants. In this picture, when a new bubble universe forms in the eternal inflation foam, it randomly selects one point on this landscape. The strength of gravity, the mass of an electron, even the number of spatial dimensions could be different in each one. In most of these universes, the constants would be wrong for complexity. A universe where the nuclear force is too weak might have no atoms. One where dark energy is too strong might rip apart before the first stars form. But in a rare bubble like ours, the numbers just happen to line up, allowing for galaxies, planets, and life. This provides a potential, if controversial, explanation for the apparent fine-tuning we observe. It is not that the universe was designed for us, but that we exist in one of the rare habitable pockets within a much vaster and more chaotic multiverse. While we currently have no way to test for these other universes directly, the idea expands the scope of reality to literally unimaginable scales, suggesting that everything we know is just a local ordinance in a cosmos of infinite variety. The ultimate fate of all we see is written into the emptiness between the stars. That void, seething with vacuum energy, is not just an empty stage but the primary actor in the cosmic finale. Dark energy, the force accelerating the expansion of the universe, is fundamentally a property of this vacuum. Its behavior dictates our long-term destiny, and the possibilities are as stark as they are profound. The most widely accepted scenario is based on the idea that this vacuum energy is a true cosmological constant, unchanging for all time. If this is correct, the universe is on a one-way trip to a state known as heat death. In this future, the expansion continues to accelerate, pushing galaxies apart until each is isolated in its own pocket of darkness. Stars will burn out, black holes will slowly evaporate, and over trillions upon trillions of years, the universe will approach a state of absolute zero temperature and maximum entropy. It becomes a cold, dark, and nearly uniform sea of diluted particles, a quiet end to a spectacular story. Yet there is a far more dramatic and terrifying alternative. What if our vacuum is not in its true, lowest energy state, but is instead trapped in a false vacuum? Picture a ball resting in a small dip on the side of a tall mountain. It seems stable, but the entire mountain represents a lower energy state. Our universe could be that ball, sitting in a precarious, temporary valley of stability. At any moment, a quantum fluctuation could cause a bubble of true vacuum to spontaneously form somewhere in space. This bubble would then expand at the speed of light, its walls rewriting the very laws of physics as they pass. The phase transition would be absolute. The fundamental constants that govern forces and particles would change instantly. Atoms would disintegrate, nuclei would dissolve, and all structure would be erased in a flash. There would be no warning because the wall of the new reality moves at light speed. One moment the universe would exist as we know it, and the next everything would be gone, replaced by a new, alien state of existence governed by different rules. This means the stability of our entire cosmos, the continuity of time and matter, hinges on the delicate, quantum-level configuration of nothingness itself. We are living on borrowed time in a universe that might be fundamentally unstable, with the final curtain call waiting in the quiet hum of empty space. Gravity was the last architect to arrive at the construction site of the cosmos. In those first moments of unimaginable heat, all the forces of nature were fused into a single, primordial superforce. There was no distinction between the glue that holds an atom together and the pull that shapes a galaxy. But as the universe expanded and cooled, this perfect symmetry began to shatter in a sequence of cosmic phase transitions. The first force to peel away was gravity itself. This happened almost immediately at the staggering energy of the Planck scale. Yet this early separation is deeply ironic. While gravity was the first to become distinct, it was the last to truly make its presence felt on the cosmic stage. The other forces emerged with immense power, ready to govern the realm of the very small. The strong nuclear force locked quarks into protons and neutrons. Then, the electroweak force split into the electromagnetic force and the weak nuclear force, defining the rules of chemistry and radioactive decay. These forces built the atomic world, but they are short-range actors. Gravity, in contrast, is incredibly weak. A tiny magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. Because of this profound weakness, gravity had to wait. It works through patience and accumulation. Its influence is only felt when vast amounts of matter can gather, allowing its tiny, persistent tug to add up over immense distances. So while the other forces were busy forging the ingredients, gravity lingered in the background, a whisper waiting to become a roar. It took hundreds of millions of years for its cumulative pull to finally overcome the expansion of space, allowing dark matter to collapse into halos, and for those halos to draw in the gas that would become the first galaxies. Gravity's late arrival as the dominant large-scale force is why the universe had to cool and grow vast before its grandest structures could ever begin to form. Our most powerful telescopes act as true time machines. By gathering light that has journeyed across the cosmos for billions of years, they grant us a visual record of 94% of the universe's entire history. We can observe galaxies so distant that their light has been traveling for over 13.4 billion years, meaning we see them not as they are today, but as they were when the cosmos was a mere infant, just 400 to 500 million years old. This is not an artist's impression or a computer simulation. It is direct observation, a series of snapshots from the deep past that chronicle the grand narrative of cosmic evolution. The only chapters missing from our family album are the very first ones. The universe's opening act, the first 380,000 years before the release of the cosmic microwave background, is a blur of opaque plasma forever hidden from our view. And the truly primordial instants, the Planck epoch and the fire of inflation, remain realms of pure theory, their details lost to the violent stretching of space-time itself. Yet what remains visible is staggering. We have a near-complete film reel of the universe growing up, from its first faint stellar sparks to the majestic galactic cities that fill the void today. This incredible vantage point transforms astronomy from mere stargazing into a form of cosmic archaeology. We are not just looking out into space, we are peering back through the layers of time, piecing together the epic story of how a seething, formless beginning gave rise to the complex and beautiful cosmos we now call home. This journey through 25 forgotten facts reveals a cosmos of breathtaking complexity. We have traveled from a universe smaller than an atom to one that is likely infinite, from a single unified force to a reality ruled by dark and unseen powers. Each piece of the puzzle, from the quantum seeds of galaxies to the echo of cosmic sound, shows us that the classic Big Bang story is just the opening paragraph of a much richer, stranger epic. The true narrative is woven from quantum fluctuations stretched to cosmic scales, from the ghostly grip of dark matter and the repulsive push of dark energy. We are left staring into the abyss of timelessness, wondering about the universe that came before our own and the infinite realms that lie forever beyond our horizon. In this grand cosmic drama, we occupy a profoundly humble position. We are temporary beings on a fragile world, a pale blue dot adrift in an immense ocean of stars and silence. Yet we possess a truly staggering gift, the consciousness to look up and question, to piece together the clues and comprehend the universe's magnificent history. We are the universe awakening to itself. This story is not finished. New mysteries emerge with every discovery. So we turn the question to you: which of these 25 facts reshaped your understanding of reality the most? Was it the universe born from a quantum bounce, the holographic nature of reality, or the simple, profound truth that you are made of stardust? Share your thoughts in the comments below, and if you are hungry for more deep dives into the secrets of space and time, be sure to subscribe. The cosmos has many more stories to tell.